Good evening, sir. Good evening, sir.
Hello,
Good evening, sir.
good evening. So, will there be more people joining? Is both the persons are same or different? We'll wait for more couple of minutes, then we'll start. Maybe if somebody will join. Can you see my slides? Hello. Can you see my slides? Hello.
Yes, sir.
Okay. Okay. So, am I audible?
Yes, sir.
Okay, fine. Um, so let's begin our today's class. And uh, good evening, everyone. And welcome to the week 5 of doubt and problem solving sessions in the course of carbon materials and manufacturing. So I'm Saurabh Soni, and today we'll be discussing mainly about whatever covered in week 5. But before taking up the questions, I would like to go thoroughly with the slides that whatever the teacher has explained in the slides or in the lectures. So it would be a more helpful for you, even for when you will be solving your assignments. So we'll be going one by one through the slides from the startings, like in week 5, and then we'll try to solve some questions also. So Firstly, we'll take up clear all the concepts, and meanwhile, I will also be discussing if something will come up, some new terms or something which you are not aware, and also you can ask in between too. So let's begin. So let's start from the first slides. So first thing is your glassy carbon. Maybe you have in my previous classes also I have used this terms glassy carbon, but how many of you remember that what is glassy carbon? If you had attended my previous lectures, or how it looks, or for what application I told you that we can use this glassy carbon. If you remember that the chart where I have shown you that all these structures, glassy carbons, carbon nanotubes. When I
Classic
was
carbon is
yes,
non-graphitizing and it can be used as an electrode material.
okay, yes, we can use that. So basically, I have discussed this glassy carbon and all. Then I was discussing all types of carbon and graphitizing, non-graphitizing carbon and all. So basically, two important non-graphitizing industrial carbon material is glass-like and activated. You might have heard. So again, the questions come. So what I will do in this lectures? Sometimes it happens when I am ahead or when I'm in latest lectures. Then usually you start forgetting your previous concepts. So here again the term came, which is a non-graphitizing. So does anybody I mean remember that what does it mean? I mean non-graphitizing and graphitizing. Can anybody say something on it?
Graphitizing carbon basically is like graphite-like structure, so graphite AB structure, whereas non-graphitizing carbon will include certain portion of AB structure with another curved carbon or amorphous type of carbon structures.
Okay, that is fine. Anybody else who would like to give some? It's very simple. So who is this another people? Khush. I can see here one more people. Is this the same idea of yours who was answering or
No, no, no.
no? Okay. Okay, fine. Oh, so it's very simple. See, the non-graphitizing is what that cannot be converted into graphite. Even if you are taking it at a very high temperature, you won't be able to convert that in graphite. So that is a non-graphitizing material. Graphitizing material. I mean, basically, wait. Yeah, non-graphitizing. Okay, so it cannot convert to graphite even if you will give a very high temperature, then also it cannot convert. So how you will know that it cannot convert? Because it will not, I mean, no any crystal structure formation, no any crystal formation, so you won't get any peak. Okay, so that's what I discussed in our last lectures if you have attended. So if you will do that like a graphitizing material, so you will get some XRD peaks like this. Okay, but for non-graphitizing you will get something like a hump. because it will not make a crystal, right? Similarly, for the graphitizing, it can easily convert to graphite material. So which is called the graphitizing, right? So here you will get something like this kind of a XRD peak. Okay. So then the glass-like carbon is also known as glassy and vitreous carbon, which is IUPAC name is glass-like. So it is obtained by the heat treatment of resins and PVDC, polyvinylidene chloride, and some acrylates. Okay, so you have to do some heat treatments, then you will get this glassy carbon. So atomically flat and shiny surface. So how it appears when the questions can came that what is the physical appearance of this glassy carbon. So it is very shiny and atomically it is flat, and it is because of the coking. If you have seen our last lectures, then you might know the term called coking and carrying. So can anybody know that what is this coking and carrying? What is coking?
Cooking is heat treatment in such a manner that it passes the phase transformation from solid to liquid occurs.
Okay,
And charring is when this is not occurred. So the product, when char product is formed, it is highly porous.
okay, fine. Yeah. So here there is no any liquidus or the semi-solid state. Okay, and in there coking, there you will have that. So in mostly in the case of this, so mostly in the case of this, you will get a porous kind of a structure. But here in this case, what you will get a solid structure. Okay, so this is the difference. So the questions may come if you are looking for any materials, and the most is important thing is your properties, right? So what are its properties? So first thing is shatters on breaking, but features short range graphitic ordering. So here if you know that there is terms called like a short, wait, somebody wants to join. Okay, so yeah, so yeah, shatters on breaking, physically amorphous. Okay, so this is an amorphous material. Again, the term which I would like to correlate is again two term. Why it is amorphous? Because it is a non-graphitizing material, right? It is a non-graphitizing material. So even though if it will be a non-graphitizing material, you can't make it a crystal out of it. Even if you will give a very high temperature, you cannot get a crystal. So that's why it is a amorphous. Okay, because it is a non-graphitizing. So usually what will happen, it will shatters when you will apply some forces or when you try to break. But the feature sort and graphitic ordering, the graphitic ordering, if you remember when I was discussing about the graphitic ordering, so in previous lectures, so there is some ordering, so basically it attains a short range. Okay, and then the second is has micro porosity, closed pores of size 2 to 5 nanometer, and low density. It has a very low density of 1.3 to 1.5, but it also has a micro porosity. Okay, like carrying in we get some porous, but here what you will find different is that the pore size of this carbon material is very low. Just a 2 to 5, but in some in some applications you do require or you do need a porous kind of a material. So in that application, this material is very, very suitable. The third one is impermeable to glass and liquid. Fourth one is high electrochemical stability. Okay, so that's why you can do electrochemical studies because it has a very good stability and it does not participate in the electrochemical reaction in a wide range of applied voltage. Stability window depends upon the surrounding medium. And there is an excellent thermal conductivity and thermal shock resistance. Okay, so you may know the thermal conductivity, but can anybody tell me that what is this term thermal shock resistance? What is this?
The ability of material to withstand sudden change in thermal energy.
Yes, yes. So basically what it does is like that. Suppose suppose I have one material and I'm heating that material. Fine. Okay, let me explain it like this. uh, yeah, suppose there is one bath, or let's say I can say some furnace, and I have some material. This is a furnace and it has a very high temperature. Okay, and in the one side I will have a liquid nitrogen, and you know the temperature. Anybody know what is the temperature of liquid nitrogen or any range?
77 Kelvin or minus
Yes, around,
164
if you
Kelvin.
will say in Kelvin, that is around usually less than 150 or 170 degrees centigrade, in the region of 190, 180, you can say. So, so here, suppose what you will do, you will again, I mean, take out your material and you will dip in the liquid nitrogen. Then what will happen? Here the temperature was very high, suppose let's say 100 to 150, and then you are putting your samples below minus 150, right? So your material should have that much capability to attaining such thermal shock. I mean, the material is in the shock, and which kind of a shock? It is a thermal, because here you are putting your material from a very, very high temperature to very, very, very low temperature, less than minus 150 degrees centigrade. So your material should have the capability of attaining this kind of a thermal shock from a very high temperature to a very low temperature, right? So this is called the thermal shock resistance. Okay, with minimal expansion. So sometimes when you do the thermal shock, your materials might break or it can shatter. Thermal expansion coefficient is this. Good electrical conductivity, mostly in the carbon. I have discussed that it has a very, very good conductivity, and the resistivity you can say in the range of micro ohm, so which is very good. Good mechanical strength. Young modulus is in the range of 20 to 40. This is some factual data which you might require when you will do some problem solving. So regarding glassy carbon and corrosion resistance, one can boil concentrated acid in it. So also it has a good corrosion resistance. And the term came here is the biocompatible. Okay, so maybe something new, not new, but it is, maybe you have heard this term biocompatible. So what does this mean, biocompatible?
Uh, this classic carbon is being used as a base electrode material for biosensors, or basically non-invasive sensing, by
No,
just placing
that
sensors in the body.
no, that
That
is
is
fine.
this.
Obviously, because of its biocompatibility, only we are able to use in the something is applications which is related to that. But what does this term means, biocompatible? when somebody will say, is this material is biocompatible, then you, I mean, what you will, I mean, what you will figure out from that, you know, it's
It
very
will not interact with the environment in the biological system, such as uh, if we are placing environment inside our body is different than the external environment, so it should not interact with the environment within our body.
okay, let's do it in this way. Do you know the bone implant?
Yes, sir.
Okay, which we use in our bone fracture and all. Okay, so let's say I have this bone, and this bone is, the bone was like this, but it fractured here. Okay, so I want to put some bone implant here so that this bone can, attach. So this should have a biocompatible. Now I will say you that what exactly means by the biocompatible. Obviously, when you will put any something inside your body, when you will do some in vivo study or in vitro study, then it will be in non-contact with your environment. But the thing is, what will happen here? Even if, suppose if your material is biocompatible, okay, then you will have a lot of cells. Okay, in human body cells you will have a lot of cells, suppose muscle cells. So let's say you will have something like some muscle cells, you will have some bone cells. So in bone cells, if I remember, MC3T3, one kind of a bone cells. Similarly, there is one muscle cells, you will have a lot of cells in your body. So while growing and when you will put your material, so such that the cells, should not die because you are putting the implant. So that should be incompatibility. Okay. So here, when you will do, your cells should be incompatibility with sorry, incompatibility with your material that you have inserted externally. So then only you can say, oh, your material is a biocompatible because it is compatible inside your body. It is not giving any toxic things. I mean, suppose if you are putting these materials and it started reacting with some of your body fluids and all, and it starts corroding, and after, as a result, it starts giving any toxic material, then you can't say that this is a biocompatible because it is giving a adverse effect. So it should be a compatible, it should be not give any toxic things. So then only you can say that your material is a biocompatible. Understood?
Yes, sir.
Okay, now is it easy for you to understand? Right?
Yes, sir.
Now that does not degrade. It is biocompatible, but it is not a biodegradable. It means what? Suppose if you have put any material, again the same thing here. So after some time, it will not degrade. It will be as it is like that. So you have to remove this material externally and has no adverse effect on the biological tissues, which I have explained just right here. What I was explaining, suppose your if you have put your material in your body, suppose if you have put here, then there won't be any adverse effect with your tissues. There are a lot of cells and tissues. So because of the adverse, it can give you a toxic some toxic component, but it is not having any this kind of a effect, adverse effect, you can say. So that's why it is a biocompatible but not a biodegradable. Remember this thing. So you can only use this kind of a material where you require a biocompatibility, not biodegradability. Clear?
Yes, sir.
Okay. So I hope this slide is pretty much clear. So um, again the next is again regarding that. So in the glassy carbon, here you can say in camera lens mold fabrication. So you can see this mold, right? So this is a large scale application of your glassy light. So in the previous slide, I you have seen that it is a shiny. When you will see this here, it appearance is what? Shiny surface. So here it also, you can see this surface is looks very shiny when you will see any cameras outer body molding. So the large scale industrial application of glass like carbon is what? High temperature parts of a furnace. So usually what materials we use as a crucible?
Silica or aluminum.
Yeah, silica, aluminum, tungsten and all. Why? Because it can sustain a very high temperature, right? So similarly here also high temperature parts usually when you will go for any muffle furnace, you can use this. You can use this in the normal this high temperature furnace where your material require high temperature. Lining in industrial vessels that contain a corrosive chemicals, okay, and have hours. So in industrial vessels, suppose this is a kind of a vessel, so there you can use for the lining in what you can use this kind of material in the lining like this in the body, because it is in the previous slide we got to know that it is a corrosion
Corrosion resistance.
resistance. Yes, right. So that's why you can use this for the these applications. Now the electrodes, like as you said, we can use this as a reference electrode or the various electrochemical applications also. We can use this, and we can use this as a bone and tooth implant, load bearing joints in human body. Okay, so when you will have any kind of a fracture like a knee joint or the hip joint or anywhere, you can use this material as a biomaterial. Why? Because as I have explained, because of its biocompatibility property, we can use this as a bone implant material. Okay, mortar brushes, we can use this. Glass molding, camera lens mold, like as I showed in this image, high temperature molds, so we can use this for this camera mold also. Can be used as a reinforcement material in composites and in micro and nano device, electromechanical system, various electrode, and you can also use this as a sensors. Industrial manufacturing process is how is that a resin precursor is powdered, packed and heat treated. Okay, then the solid resin structure can also be heat treated. Two more steps may be involved in heat treatment. Similar to graphite manufacture, pore filling is important. Resin may be refilled inside the pores after low temperature treatment, and final temperature are more than 25 degrees in the case of industrial applications. So these are some manufacturing process which you can also find in the lectures, or you can watch any YouTube videos, or there are a lot of industrial videos which are available. There you can find that how I mean, what are the steps involved in the manufacturing. So this is all the industrial purpose. You should know that if you want to do any industrial exposure, then it might require you. Clear?
Yes, sir.
Okay, yeah. Non-graphitizing carbon microstructure. So, what you observed by this micrograph, or by this, what to say, image? Can you say, like, what is this image, or what information you can obtain from this image as a metallurgist or the material scientist?
They are like fiber-like structure is observed,
Hmm.
and it is like a network of the of carbon, which is
Hmm.
but without any definite arrangement.
Okay. What else?
Sir,
Huh?
in that image of TM,
Huh?
there is like in the left hand side image, the upper part there is a network kind of observation,
Huh?
but in the lower right half it is like just plain part.
Hmm.
So is that because of sample preparation, or like basically I still don't understand how to interpret TM images. That's why I'm asking this
Okay.
question.
Okay. Okay. Wait. I'll explain this. Hmm. Fine. So this is just an image. I mean, it's just on the basis of the where you are taking your image. It's just a placing. Okay. So I do not know that whether the material sample preparation is good or not good. But the thing is, what I observed, or what I can say from this image is, first thing is non-graphitizing. Okay. So you can't, this is look like a very random arrangement. Okay. It is not looking like a crystal. You can't say any, crystal. Crystal structure, you can say. It is more or like a amorphous. So this is by looks, you can see here, this here and here, this is very, I mean, random. I mean, no any specific arrangement. When you will see the graphite, you will see some shades, some flags, kind of a thing. But here it is a very very random things, kind of a thing. Okay. But when you will see any graphite image, or you can just google, you can see any sheets, or kind of a flags, in graphite flags or graphite sheets, 2D sheets. But here it is not like it is. I do not know that what structure it is, whether it is a sheet, whether it is a flag, or whether it is something else. So here, because it is a non-graphitizing carbon, so here it is, that's why it is amorphous only. So here, the based on the broad peak. Okay, so here again, as I said that since it is a amorphous, so here you will get a this kind of a broad, sorry, it won't like this, it will be just like this broad peak. Okay, in XRD. and TM micrograph interpretation. Various models, were observed, were suggested for the microstructure of non-graphitizing carbon. Important notes is TM images are 2D projection of the 3D object. In case of carbon sheets, only the edges are visible in the micrographs. Okay, so this is point to be noted. So again, TM can directly provide the image of materials, but one can only image a very small area. So do you remember or do you know that what is the resolution of TEM image or any TM up to what you can see?
Uh, you can see like uh, 100 nanometer.
100 nanometer, but here in front of you the scale bar is 5 nanometer. You are seeing a 5 nanometer feature. Here you just read this. Scale bar is 5 nanometer.
Sir, there are two techniques, na? Transmission electron microscopy and high resolution transmission electron microscopy.
Yeah, they are just a ties because if you will use a higher voltage, lower voltage, and some more configurations, because now in equipments a lot of configurations are coming. But overall generic point of view, if you will see that you can see in a, if your materials are a very well prepared, then you can see some atomic arrangements also by using your TEM images. Okay, so even the less than the nanometer also you can see it has a very very high resolution. Other techniques such as XRD, which indicates the crystallite size and the thickness, is used for obtaining a global average value of crystallinity. So even if you have crystalline material, you can observe by this XRD that what is its value of crystallinity. Okay, so these are some informations that we can get from our characterizations. So that's why the characterization is very important when you will deal with any kind of a material. Okay.
Yes, sir.
So now the non-graphitizing carbon microstructural models. So here the model one you can say in image A, given by the Rosalind Franklin in 1951. So based on XRD details analysis they have done. First, a classification of polymeric carbon into graphitizing and non-graphitizing. Okay, so what they did, firstly they classify the polymeric carbon into two, graphitizing. Just I have explained. I mean, your polymer. There is your polymer. So what they have just classified is the graphitizing, and the second one is non-graphitizing. So it cannot convert into graphite. It can convert into graphite, which I have already said. Okay. Then randomly oriented graphitic crystallite suggested explains porosity in the Ng carbons. Okay, so as I said that in this here, what you will get a amorphous, also it is amorphous, you will get a porous kind of a structure. So that's why the porosity will present here. Cross links not explained, no curve carbon suggested. So yeah, again, which I have already taught you that what is curved carbon, if you remember.
Carbon which has like one non-sp2 bonded sheet, like non there's such as CNT or fullerene where a 5 member rings are there.
Okay. So what is curved carbon? I mean, what basically definition? Yeah, that is right. The fullerene. CNT.
They make an angle with the unhybridized orbital. I don't clearly remember the name of that, but that it's arranged generally in planar carbons
Mm.
perpendicular, but in curved carbons, that curved plane is making some angle with the pz orbital of bonding.
Yes. So it is a matter of angle. So like here in that case, you will have some 90-degree or 180-degree then, but it is in the range of I mean, in that in between somewhere. That's why where you will get a curved carbon. Okay. Then the model 2 came here in image B. You can see here. So this is given by the J.M. Jenkins and K. Kawamura in 1971. Based on they have given in XRD and TM, long entangled graphenic ribbon like structure. Here you can see it is like a more tangled. Here it is more like a non graphitic kind of a things, not arranged. But here it's like a ribbon, graphenic ribbon like a structure they have suggested. See, long tangled. It is tangled. Long ribbons are not energetically favorable. Defects, curved carbons, absence here, may have seen a misinterpretation of TM images, and the LA considerations are not clear. So, so then this is the image of a model 3. Here you can see a very beautiful this arrangements. So based on the TM, some fullerene like structure suggested. Here you can see some curved, this is curved. This is, you can see here like this is like this, some curved. And then the stacking graphitic regions and larger sheets ignored, discrete segments suggested. Okay, so here you can see a discrete segments are here. I mean, it's not very continuous, it's all separated. But yeah, this is like a more kind of a fullerene kind of a structure. Then the model 4 came by Swati Sharma et al. In 2018. I think she's the teacher of this course that who is teaching. So the coexistence of curved and the flat structure with a wide range of size, in situ studies of carbonization rather than only final material, and very complex pictorial representation model limited to polymers and undergo poking. Okay, so maybe later we can see. I think this is, yeah, this is that. So we'll see this. So in situ TEM studies of polymer to carbon conversion. So during pyrolysis, large polymer molecules are dissociated to form fragments of hydrocarbon. Okay. So I explained like in the last class, what is pyrolysis?
Sir,
Huh?
hello.
Huh?
Can you repeat the question because I had some network issue?
Okay.
Couldn't
So
get
this
that.
question is, they said that during pyrolysis. So what is pyrolysis? I mean, I explained last slide, last lectures. So the
Uh,
treat.
Pyrolysis is heat treatment
Hmm.
uh, up to 1000 or 1200 degrees centigrade,
Hmm.
where basically the
Hello.
PVC or something is removed, and the material converts into carbon but not graphite.
Okay. So here, yeah, it is a one kind of a thermal treatment where you will require some temperature. So the large polymer molecules are dissociated to form a fragments at harp. Suppose you will have a very something like a large polymer molecules. So they, after a pyrolysis, it will make a fragments of a hydrocarbon. Okay. Now, when hydrogen is released, this fragments convert into carbon. So now it is a hydrocarbon. After that, hydrogen will release. Now what will remain? Only carbon. So convert into carbon fragments, but with multiple 5 and 7 membered ring defect, etc., which lead to curved carbon structure. Okay, so there will be a lot of carbon membered ring, so that will defects will also present. So that because of this only carbon will be present, so that will leads to, I mean, give you a curved carbon. Now the some structure can have such a long curvature that they become spherical. Okay, so if you will have, I mean, a very long carbon structure, then instead of the curvature, it can become a complete spherical. In this study, a very thin film of a resin was heated. So here, what they did is they have taken thin film of resin and they heat that very high temperature inside the vacuum chamber. Okay, of the TM setup and heated via Joule heating. And then they have observed images were taken at the interval of the 20 degrees centigrade. Okay, curved carbon structure were observed at the 900 degrees centigrade. Here you can see. So where this is the 900 here. You can see something like this. Maybe this is, I also do not interpret this. But yeah, here it is more like this straight kind of, but here this is like more like a curved carbon, and some circular looking structure can also be discs rather than the spheres. Okay, they are like a disc rather than the spheres. Here also you can see something, maybe they are talking about this. I do not understand clearly this image, but yeah, maybe like this. So important consideration is beam damage. Beam can damage during the imaging, so you have to be very careful when you are doing this imaging, because here the high temperature is giving like till maybe more than the 900, and the interpretation of this TM image is very important. So even though if I will give you like, even though also here I could not be able to completely interpret this TM image because I do not have any expertise in that. But if you are very well aware or of this your micro imaging techniques like SCM or the TM, or there are some more like FESCM, FIBCM, so you will probably can able to handle this kind of imaging, and you will get to know better observation by this. Then the structural changes on cooling. Okay, so suppose if you will do like a heat treatment, suppose your material is at suppose this is your material, suppose it is at certain temperature T1, and if I'm suddenly taking this temperature to T2, and then there is another temperature T3. So there must be, if this is like a metal, then I can see in the perspective of the metal there is like a grains and all. Then if you will go from the one temperature to another, there is something new will come, or some new formation of a grain boundary, or something will some another thing will come when you will go to another temperature, because it's material property, because the materials tends to behave differently in certain temperature. So that's why it is very important to to see this, what are the structural changes upon cooling or heating, in order to analyze your material properly. Okay, so a resin converting into a, so here you can see this is like a resin converting into a glass like carbon on inert heat treatment inside a TM chamber. This scale is 1 nanometer. Here you can see, we can see this scale is 1 nanometer. I said, resolution is even less than, you can see 1 nanometer, you can see. Okay, and this is in the degree centigrade. This is all.
Okay, sir.
Okay, so this you can study in your, if you will have anything to this kind of a material, you can do some in situ TM studies. You can vary your temperature, you can see that what are the structural changes are happening inside your material, and on the basis of that you can, give some kind of a, this kind of a model.
Okay, sir.
Okay, so let me take a 2-3 minutes break because today I'm little sick, and then I'll again resume. Okay, so let's resume. Okay, so here um, this slide is mainly explaining again about this glassy carbon. So here, due to the release of relatively high fraction of tar and gases, it is important to have a thin walls. Annealing of byproduct is very important during the pyrolysis. Okay, so when you will be doing any pyrolysis heat treatment, then um, the annealing of these byproducts are very important. High surface area of the structure also helps in crystalline order to some extent, and micropores are not annealed. Wall thickness in a industrial application is typically less than the 5 mm you will get. For this thickness, process temperature should be more than the 2500 must be used. Cooling rate is very important. Pressure, what are the pressures that you are using during your process, and what are the environment that I mean some gases you are using, you are doing in a vacuum or in some inert atmosphere. So these all are some influencing factor that can affect the microstructure and your properties of the material. So let's say suppose if you are using some temperature T1, your process temperature is to T1, but you are not using T1, you are using a T2, then the properties of your material might vary because of this temperature. And the cooling rate is also important. The cooling rate is what, suppose if you are after processing, if you are cool down your material, then on what rate you are doing annealing or normalizing or quenching. So do you know the difference between these three?
Yes, sir.
What is annealing?
Annealing, in terms of steel, I know the difference.
Hmm.
So, in annealing treatment, basically we convert austenite to pearlite structure by slow cooling of the after heating. There is a slow cooling rate,
Yes.
whereas in normalizing, the cooling rate is a bit higher, and we can get more. There is like uh, fine pearlite structure is formed,
Hmm.
and for quenching, also called as Martensic transformation, there is sudden cooling of the steel sample,
Hmm.
which causes uh, alpha ferrite and cementite to separate. uh, like cementite is present in alpha ferrite in certain places,
Hmm.
pores.
Okay. Fine. But okay. Let me give you a very simple that what is the difference. So first thing is your annealing. You put your sample in the furnace, suppose this is your furnace, and you allow it to cool inside the furnace only. You do not require this sample to come out of the furnace. You just switch off the furnace and let it very slow cooling. Okay, this is annealing.
Yes,
Normalizing is
sir.
what? You are taking out this sample in the air and you are cooling it, so it is normalizing. Quenching is what? You are taking out the sample and you are dipping this inside the water or any other medium. Got it? So this is the
Yes, sir.
basic difference between the annealing, normalizing, and the quenching, where you will have to expose your material in certain atmosphere in order to get some specific properties and microstructures. So this is the temperature or cooling rate, pressure, environment influence can affect the microstructures. The small resins particles help in increasing the surface area. There are some common precursors like phenol formaldehyde and furan resins. Phenol formaldehyde resins prepared by mixing phenol and formaldehyde you can prepare. There are two types, Resolve and Novelac. Here the phenol to formaldehyde ratio is more than 1, but here it is less than 1. Furan resins, here you can class of polymers with furan rings as primary structure. I also do not have expertise in this, that how they look. It's more like a chemistry things. Furan resin can also be prepared using biodegradable waste. So these are some factual things, that what it consists and how it prepares. So it is mainly telling about that. Okay.
Yes, sir.
Now the problems with this GC manufacturing, glass GC is what? Glassy carbon or the glass like carbon. So here the high cost of raw material. Okay. So this is the problem. So it will, what it will do, it will increase the cost of your material, because even if you will get the raw material at very high cost, your end product will also very costly. Energy consuming manufacturing. So here energy, why? Because it requires a high temperature like a pyrolysis, and also you will require a very high energy. Dimensional shrinkage. So yeah, this can, I mean, reduce the dimension when you will do this thing. So maybe it shrink when it cools down, and the porosity, you will get a porous kind of a structure. Environmental concerns is also there. So this is something that is the problem here. So what are the solutions here? So optimizing properties based on the application. So what application? Suppose one application we say we used in the our camera mode. Okay. So here we can use this inside our camera mode. I'm not good in the drawing, but here you can see. Suppose I do not know, but yeah, in the camera mode you can what specific property you want, or something different like electrodes, or in electrochemical, what are the applications you want. So you can optimize based on the applications. Development of inexpensive resins. So here you can use some inexpensive resins that can from the waste material. So what it will do, it will reduce the cost of your material. Okay. Mixing catalyst is catalyst in precursors that will improve the crystallinity, and it may compromise purity of your material, and carbon materials can be used as a catalyst also. Structure shape optimization, factoring in the dimensional shrinkage, increase in surface area of precursors, and micro nanostructures and device because of its high surface area and the less materials are required. So we can use this in this. So these are some pretty good solutions, that in order to avoid your problems during the manufacturing and during the applications. So yeah, so this is that. So till here, this is like a glassy carbon. So is it clear, or you want to ask something regarding this glassy carbon, how it uses applications, and whatever I have discussed in the slides?
It is clear, sir.
Okay, fine. Okay, so pyrolysis of solid aromatic hydrocarbon. So in your basics, plus one, plus two, types of hydrocarbons, aromatic hydrocarbons, aliphatic hydrocarbons. You can see there that what are the difference and all. So here it is mainly talking about the solid aromatic hydrocarbon. Pyrolysis, again the term came pyrolysis. So some thermal treatment is involved here. Okay, just a second. Somebody's. Yeah, sorry for. Yeah. So pyrolysis of this solid aromatic hydrocarbon such as polymers here is used for. So the first thing is the bulk industrial graphite or the glass like and the porous carbon manufacturing, carbon fiber, carbon composites manufacturing, micro scale and nano device. Other applications, pyrolysis, mass spectroscopy. I do not know basically thoroughly about this, what kind of this mass spectroscopy is, but I know mass spectroscopy, but do not know the pyrolysis mass spectroscopy. Waste treatment also. In all cases, a large number of chemical reactions take place during the initial 700 C. Like I told you. So you have to give some thermal treatment. So a large number of chemical reactions take place during its initial temperatures. So some pyrolysis by products are collected. Okay, so what you will do when you will do any suppose let's say any heat treatment, then what will happen? So suppose your material, then you will get as a exposure to the temperature, you will get some byproduct. Okay, so this byproduct you can collect, and it can be also used for some application. Suppose for an example, if you will go to steel industries, then after your iron making process you will get some slag. So you will get a lot of things, you will get ammonia and all. So you can get in the plant also, it can from the steel industries or the hot metal, you can get some slag. So these are like a byproducts that you can use in some certain applications. And the mechanism, am I audible? Had I unmuted? Okay, am I audible, right? Hello, hello, hello.
Yes, sir, you're audible.
Oh, uh, okay, fine. So a mechanism is accordingly proposed in case large scale structure pyrolysis temperatures are higher compared to the micro nanoscale device. Sorry. If the structures are attached to a substrate, they displace less shrinkage from certain surface. Okay, yeah. So this is a very good kind of a. Okay, so this is a AFM tip made of a resist carbonized at 900 degrees. So this is, you can see this tip. Do you know this? Do you know
Yes,
this?
AFM is atomic force microscopy, no?
Huh?
Yes, sir.
What is this?
This is that um, AFM tip which is manufactured, which is used to find the surface roughness of a material.
Okay. Yeah. So do you know like have you seen AFM equipment?
Yes, I have seen.
Yeah. So AFM is basically there will be like a tip kind of a structure. So this is like a tip you can see in a very basic manner. So like it will if there is some surface roughness, then it can go and hit, and it can scan a certain place. So it will give you some roughness profile of your material. Okay, so this is like a distance, this is your surface roughness. So here this is like a non-uniform shrinkage in structure attached to the substrate, and this is bending due to excessive poking. So this is also a very good, I think, SCM images if I'm correct. I do not know. Yeah. Now the characterization of the pyrolysis products. So after you will do a pyrolysis treatment, you will get the product. So in order to know, the property of certain, that how can we use that material, and what can be put with the applications, you can use your product. So the first thing is polymer here. So this polymer will go for your pyrolysis. Okay, pyrolysis. So here they are giving the temperature up to 700 degrees centigrade. Then thermogravity. So here what you can do as a TGA, thermogravimetric analysis, gas chromatography, mass spectroscopy. So what you will get by TGA?
Degradation temperature,
Huh?
thermal degradation of the sample. Like if there are more than one uh, kind of chemical species, they degrade at different points. So TGA curve basically will show that different degradations.
Okay. Yeah. So basically this is like a TGA. So here you will have some temperature which is going like this, and here this is a reduction in your mass, or something you can say the weight loss in percentage. Okay, so here what it will give something like this kind of a structure. Sorry, it's not like this, it's just like this. So what does this mean is that your material is at room temperature, and it is behaving like at certain temperature it loses some like a water and all, some moisture if it is present. Then different, if it has something more, then it can degrade and it will completely, at very high temperature it will degrade properly. So yeah, it is correct, it is giving a thermal. When you are exposing your material to the high temperature, then at till what temperature it can sustain, and at what temperature it starts to degrade. So it is basically telling about that. This is the gas chromatography. So what are the gases which are obtaining as a byproducts from your material. So it is mainly saying about that. Mass spectroscopy, I do not know the very specifically about that because I have never done this MS. And the pyrolysis is, suppose here you are getting a synthetic gas, pyrolysis residue, pyrolysis oil tar. Okay, so here you can do of this again the GC mass spectroscopy, molecular spectroscopy. I think here you will find something elements which are present in mass and molecular spectroscopy. What are the elements present in your product? Then you will go for this functionalization of the uh, residue after the pyrolysis. So there are two types, soluble and the insoluble pyrolysis. So this for the if your material I mean residue is soluble, then you can go for the this boiling analysis, thin film chromatography, molecular spectroscopy, NMR. So NMR is also one kind of a characterization. ESR, electron spin resonance, XRD. So these are a very good set of characterization. So basically, when you will see any kind of a good research paper, so they must do this kind of a characterization in order to prove the property and what are the specification they want. Because these are the some because I'm also not very experts in this, all the like for the brief I can say you, please read that. Do you know what this NMR do? What NMR does?
NMR is nuclear magnetic resonance. So basically, the nucleus of certain elements which have like carbon 13 or hydrogen for that matter, they when they are exposed to a high magnetic field,
Hmm.
they align and de-align. So depending on the applied field, the alignment and the time of relaxation varies. So which we can find out that how much quantity of that, like how is that material present over there or not, like.
Hmm. Okay. And do you know this ESR?
ESR is similar to NMR, but here basically electron spin technique is used. So NMR exploits the nuclear spin of the nuclear moment, magnetic moment, whereas ESR, there is a generally for paramagnetic sample we use ESR technique, where the alignment of the paramagnetic poles are towards a field.
Okay. I think here we applied some light and all, right? Some light and dark, then you will get some peak if your particles are how they are behaving. I do not know, but I have seen people do.
ESR uses microwave radiation as a trigger, whereas
Okay.
NMR uses radio frequency.
Do you use these techniques?
I haven't used these techniques, but I have learnt about them.
Okay. So are you from chemistry or which background?
Material science.
Okay, okay. Yeah. So yeah. And if your this material is like a insoluble pyrolysis residue is there, then you can do the heat treatment at the high temperature, and you can take this XRD, Raman, and TGA. Do you know Raman?
Yes, sir.
What it gives?
For carbon specifically, we can find the number of layers of graphite present in a sample, graphitic layers like ID by Ig ratio. It gives a basic difference. It is based. It is an extension of IR spectroscopy, where we have Stokes and anti-Stokes lines.
Yes. So here you will get some wave number and also D, G, and 2D kind of a thing. So this is basically if your material is like a graphitic, then you can probably do your Raman spectroscopy and TGA. At last, you will get some gases or the carbons. For the carbon, you will get XRD, Raman, and the BT. So you know BT.
Yes, sir. I am aware of BET.
Okay. And then for the gases, you can do this gas analysis, gas chromatography, and mass spectroscopy. So these are some characterization techniques that, in order, if you're working in this field, then it might be helpful for you to get your things done. Now, the pyrolysis process parameters are what? What are the parameters we use? So the nature of carbon obtained from a polymer is influenced by these parameters. So first thing is temperature and the ramp rate. Okay, so there is a two things came. First thing is temperature and the ramp rate. So when you will do this, ramp rate is also somewhere related to your rate of your temp at what rate you are doing. So this is also very important. So if you're putting your material, suppose if you want to put your material at 1,000 degree centigrade, and if you are giving a 10 degree centigrade per minute. Okay, so this is your ramp rate. So in this rate, your the temperature of your furnace will starts to increase, and after some specific time it will reach to this 1000 degrees. So this is also important if you want some property. If you will reduce, if you will increase or reduce your ramp rate, suppose if you are giving 100 degrees centigrade, and in case if you are giving 1 degree centigrade, your property might vary. Structural dimensions. Okay, dwell time at high temperature. Definitely, if you are exposing your material to 1 hour or 10 hour, 20 hour, or maybe 4 to 5 days, it depends what are the properties you want. Cooling rate, again, you are taking your material to the very high temperature, let's say 1000, and if you are cooling your material 10 degree per centigrade, sorry, 10 degree per minute, or the 100 degree per minute, you will get a specific property when you will change your this cooling rate. Mechanical forces applied during the structure or the pyrolysis. So this is also in pyrolysis when you will apply some sorry, mechanical forces. Your property might vary. Chemical structure of the precursors, if you are using a oxygen containing polymer like a formaldehyde resins, furan resins, nitrogen like aromatic or the aromatic aliphatic or the aromatic, polyacrylonitrile, halogen containing polymer, sulfur containing polymer. So these are some precursors that whatever you are using. So it also give a different properties to your material. Then there is a gaseous environment. What are the gases, whether you are using inert atmosphere, or you are using oxygen, or you are using nitrogen, or you are using argon. Pre processing stabilizations, pressures applied during the pyrolysis, additive and the catalyst that you are using. Mechanism of pyrolysis is like this coking and carrying, which I explained. So carrying always yield non-graphitizing carbon, which I explained, because also you will get some porous structure, while coking can yield both graphitizing and the non-graphitizing carbon. Coking enables migration of graphenic fragments, and they may also dissociate and attach to another fragment of and overall low energy. So this is, you can say, arrangement more than one sheet interaction category. So here this is a different separate sheet, and this is a different kind of a structure. So here it is like a layer by layer. Okay. So the smaller polymer structure require, so if you lower heat treatment temperature for annealing, you don't need to go for a very high temperature annealing of the byproducts and the defects. And the defects have a higher structural energy. uh, they try to become graphitic like if there is no steric hindrance and strongly curved structures. If the structure size is in the micro or the nanometer scale, it may lead to a high graphitic content at lower temperature. Some common polymers used in fabrications can yield a high fraction of carbon, which is generally glass-like carbon. So the microfabrication, these are some basics, and they are giving some scale bar. So 1 micrometer is 10 to the power minus 6 meter. Any structure or device with its functional element smaller than 100 micrometer is known as the micro device. Okay, so if I will say that what is micro device, then any structure which is less than the 100 micrometer, that is a micro device. Nano device is what? Then 100 nanometer, less than 100 nanometer is nano device. So the micro systems or micro devices are terms. Functionality or working principles can be further divided. So MEMS is was micro electromechanical system. Okay, so here you are applying so micro electromechanical system. So here you are applying a electrical energy also, electrical and mechanical. So you will analysis both. So a class of micro that utilizes the mechanical property of the functional element to obtain electrical signals. Okay, so suppose electrical. Suppose if I have a material, this, sorry, this is my material. If I am giving it a pressure, okay, it will give you a different output. Suppose if it is a piezo, then it will give some current. It will give some electrical output. If I am applying a mechanical force here, so here this is electrical and mechanical. It means that by applying a mechanical property of this material, you will obtain a electrical signal. So this is what are electrical properties to obtain a mechanical. Here also you can give some current and you can move it, or you can get some mechanical movement. Suppose if you are applying a electrical signal and here you will start in moving this substrate like this, okay, in this direction or whatever. So by applying mechanical, so here you can see applying mechanical and getting electrical, applying electrical or getting mechanical. So these are the two combinations. So this is what, this is called the micro electromechanical system. And then the examples of this MEMS are like AFM. It is very well, in AFM. So in AFM, you will apply some mechanical forces and you will get the electrical to in order to see your piezoelectric material. So in AFM, microscopic tip, acceleration sensors. In acceleration sensors also you can do this kind of phenomena. And all MEMS and micro devices, but sorry, all memes are micro devices, but all micro devices are not memes. Okay, so other than the
Yes, sir.
memes, there are other micro devices such as battery, electrodes, biosensors, various electronic, optoelectronic, electrochemical devices. So yeah. So do you know what is this biosensor?
Yes, sir.
What is this?
Certain parameters like presence of certain chemicals in a biological system
Hmm.
can be detected by electrochemical techniques.
Hmm.
So these are various sensors which are being developed, or electrodes,
Hmm.
modified electrodes developed to sense this presence
Hmm.
of such chemicals or redox reaction taking place.
Hmm. So what can you sense by biosensors?
Amount of glucose present in the body, or amount of certain like
Hmm.
if it is receptive, like so material is receptive to glucose or some other parameters in the body like hemoglobin.
Hmm.
You can construct like formulate different sensors for different
Hmm.
chemicals.
Hmm. Yes.
It can also be used to detect the drug sensing, like in drug analysis and
Yes. Yes.
application
Right.
of drugs.
Yes. Yes. So basically, yeah, that is like that inside your body, whatever the fluids and the some formations are that you can detect by using your biosensors. Like there are many things you can do some glucose or the sweat sensing and all so like that. So these are some techniques, microfabrications. So material structure and devices. Material is the substance used for making structures, then forms a part of integrated functional unit known as device. So you know very well this is the definition of the device. And the microfabrication similar to traditional manufacturing can be performed both top down and bottom down, which we have seen in our earlier lectures. What is this top to down and down to bottom manufacturing process? This is like a reverse. And microfabrications, one may or may not utilize traditional manufacturing tools and techniques. For traditional techniques used in microfabrication are drilling, electric discharge machines, machining, electrochemical machining, and etching, film deposition, non-traditional techniques like your lithography, circ bulk, micro machining. Do you know this? What is lithography? How does this work? Lithography.
Yes, sir.
How?
Basically, lithography is exposure of the particular material to certain light or wavelength, which
Hmm.
etches your design or pattern on the material.
Hmm. Okay. So yeah, here we expose our material. So there is a positive, negative lithography and the negative. So here basically we expose our material and there are some etching. So only the part which we want to transfer that could be transferred, and the rest we can etching. So there are two types. So basically in the thin film you can see that how this lithography things work. So this is also very good techniques and a lot of latest research are going on this field. So carving patterns into materials. Okay, so suppose if you have some any lithography, you have any pattern. Suppose if you want to, this is your pattern, suppose, and in your material you want this pattern, so you can transfer the lithography is transferring of a pattern. Okay, it is a top down manufacturing, from the top to down manufacturing process. It is. Example of lithography is photolithography, yeah, electron beam lithography, e beam, x-ray lithography, nano imprint lithography. So these are some techniques. This is like a material carbon, nanomaterial carbon. This is the nanotube. This is a microelectrode array. You can see a different microelectrode. It is in the array. And now you will attach this device electrochemical sensors. Okay, so this is conductive. So here it will make this connection, and this will become, you can sense any electrochemical, electrochemical sensing you can do by using this. Okay, so this is like a top to down. Top to down, it means here you are starting from this top and you are going down. Okay, so you are, and it is like a bottom up. Bottom up means you are putting your materials from bottom and you are going up. Okay, and here you are going from down. So lithography is what? Top to down. You will start from your pattern and then it start, you will get end product. So it's like that. So yeah, mostly this I have kept for today's discussions. Not much. So
Sir,
yes,
there was a question in assignment 5
yes,
only,
okay,
numerical type.
okay,
Just a minute.
yes.
Uh, Saying a polymer undergoes 75% mass loss during carbonization at micro scale.
Hmm,
Calculate the diameter of a polymer pillar if the goal to achieve a carbon pillar of 500 nanometer
hmm,
diameter.
hmm.
Ignore shrinkage and non-uniformity along the pillar length.
Hmm.
So actually I didn't get that
Well,
question.
I also didn't get that. Can you repeat this?
Uh, it says a polymer undergoes
Hmm,
75% mass loss during carbonization at micro scale.
hmm,
Calculate the diameter of a polymer pillar
hmm.
if the goal to achieve
Huh?
a carbon pillar of 500 nanometer diameter.
Okay.
Ignore the shrinkage and non uniformity along the pillar length.
So what it is basically asking?
We have to calculate the diameter of the polymer pillar before carbonization.
Okay. So I think I have not seen any formula in this lectures. Have you seen?
No, and actually, this assignment was after these lectures only.
So I think it is probably, maybe after this you will find some formula. Maybe it is not, because I have not seen. So, but anyway, I will look into that, and I will try to solve your problem in our next lecture. Will that be okay?
Okay, sir.
Okay, no? Because maybe I have not came across this question, so probably it might be
Okay, sir.
okay. So don't worry, we'll solve that.
Yes,
Okay.
sir. And sir, one more doubt
Yes.
because this is first NPTEL course I am doing, na?
Yes.
So, like for examination purpose, like lectures are enough, or we have to go through reference material also.
No, no, no. Lectures are enough. Lectures and assignments are enough. You just properly go through all this kind of.
Okay, sir. Okay, sir.
So you are not taking any classes, or you're only taking NPTEL classes?
No, I have coursework in my institute.
Okay. So apart from that, you are doing this.
Yes, as part of coursework.
Okay. Fine. Good. Okay. So yeah, we'll meet next week.
Yes, sir.
Okay.
Thank you, sir.